The following content is supported by victoris.org.
Today we'll be going through this physics question. This question involves a disk of mass m and radius r and is held up by a light string. If the surface of the disk is smooth meaning no friction, then what is the tension in the string and what is the normal force per unit length of the string? Part 1 of part A is rather simple. What we need to notice is that the tension throughout the entire string is constant, meaning the tension here, the tension here, the tension here, the tension here are all the same value. The proof for such a claim is by considering a small segment of every part of the string. Every small segment will have tension acting on its two ends, and because the string is light, meaning that it's approximately massless, and because there is no friction, in order for this small segment of the string to be in static equilibrium, the tension at the two ends of that segment must be equal. Repeating this analysis throughout the entire string will tell us that the tension throughout the entire string is constant. Now what can we do with this information? We can now consider cutting the system at two locations. One is here and one is here. If we consider this entire part of the system to be one body, then we see that the two tensions over here are basically lifting this entire body. That would imply that 2T must equals to mg, and rearranging gives us the tension equals to mg over 2. Now even though we've calculated the tension at this location and this location, we do know that the tension throughout the entire string is the same, and hence the tension throughout over here is also mg over 2, over here is also mg over 2. That solves part 1 of the question. Now for part 2, what is the normal force per unit length that exerts on the string? When we see normal force per unit length, that tells us that the unit of the answer must be newtons per meter. There are going to be two methods to solve this part, so let's go to method 1 first. Consider this force body diagram on a small segment of the blue string over here. Let this small string subtend an angle of d theta with respect to the center, and because we know that the tension at the two ends are equal, and we also know that they subtend an angle of d theta over 2 with respect to the tangent, these two tension forces act inwards on the string, pulling it towards the center of the disk. What's counteracting this inward tension is the normal contact force. The normal contact force is written as nr d theta because I let n over here be the normal force per unit length, and that will mean that I have to multiply by a length in order to obtain a force. This length is r d theta, where r is the radius of the disk, and r d theta is the arc length of this segment over here. Now balancing forces radially will give us this equation, and applying the small angle approximation on d theta over 2 would give us this. Rearranging that will give us that the normal force per unit length is given by T over R, and because we know T is mg over 2 from the part 1, the answer is mg over 2R. Checking the units, we see that this has units of newtons per meters. Now that is the first method, which is easier, but I'll present an alternative method. Now once again, we let n be the normal force per unit length, and currently we do not know this value, but we do know that it's independent of theta from method 1. In other words, n is a constant function of theta. Now we can form an equation that looks like this, and this equation is basically saying that the normal force from all the segments of the string integrated along this semicircle is going to provide the lift for the disk. The weight of the disk is mg, and this is the summing of all the tiny contributions of normal contact forces. We have a cosine theta over here because a normal force at the angle of theta would have a vertical component of n cos theta. Now because we know n is constant with respect to theta, we can pull it out as a constant, and evaluating the integral gives us this. Rearranging will then give us the answer. Now even though method 2 was kind of redundant, it is important to note that in method 2, we are basically making use of the fact that the normal contact forces provide the lift for this disk M. Whereas in the first method, we are considering the forces on each small segment of string r d theta. In other words, method 1 used the force body diagram on each small segment of the string, whereas method 2 used the force body diagram on the disk. Now moving on to part B, if there is friction between the disk and the string, meaning that the disk is no longer smooth, and let's say the static coefficient of friction is mu, then what is the smallest possible tension in the string at the lowest point? Part B makes use of something known as the capstans equation, which basically tells you how to do calculations involving a rope where there's friction involved. We'll be deriving this formula by ourselves. Now the first step is to consider the force body diagram on each segment of the string again, but this time the tension throughout the entire string is no longer constant. Hence, tension is now a function of theta, and it varies throughout the string. Now, of course, we know that tension over here is still mg over 2. However, as soon as it starts touching the cylinder, the tension is going to decrease in this direction. And at the bottom is going to have the minimum tension. Capstan's equations would tell us how to relate the tension at these 2 points. The short answer is that the tension at this point is going to be mg over 2, and the tension at this point is going to be mg over 2 exponential of negative mu pi over 2. This exponential factor basically suppresses the value of mg over 2, and you can see that it decreases mg over 2 to a very small value. Mu has a big value, then the tension at the bottom asymptotes towards 0. Now the question is, how do we derive the Capstan's equation? By balancing forces radially, we get that the normal contact force must equal to this expression over here. N over here is short for this term. Now ignoring the second order terms, we get this. We can see that the normal contact force is still equals to the tension. However, now the normal contact force is a function of theta because the tension is no longer constant throughout the entire string. Now that I've found out the normal contact force, we can go ahead and find friction. And it's important to note that friction in general is less than equals to mu n. Friction is not always equals to mu n, and I'll explain the nuances of friction in another video. In this question though, we want to maximize friction because we want the minimum possible tension to be at the bottom. In other words, if we look at this force body diagram, we see that the larger the value of the friction, the smaller this t theta needs to be while maintaining everything in static equilibrium. This means that when we maximize friction, then t theta at the very bottom over here can be the smallest possible tension as we want it in the question. So we maximize friction and balance forces to obtain this. Rearranging gives us a differential equation for t. Now we just need to integrate both sides with the correct limits of integration, and this will give us the Capstan's equation. This t of theta equals to pi over 2 is the tension at the side of the disk, and this t of theta at 0 is the tension at the bottom of the disk. Now because from part 1 we know that the tension at the side of the disk is just mg over 2, then rearranging will give us the following value for the tension at the bottom of the disk. Hence, this is the answer we are looking for. Now remember, I had two methods for part A, part 2, and one of them involved integrating the normal contact force along the semicircle and equating it equals to the weight of this cylinder. We try to replicate that method for part B. Let's try that right now. So it looks something like that. And basically now, instead of just the normal contact force providing the lift required to lift the mass, we actually have the friction coming along to help out. Now the friction is given by mu n, which is also mu t because n is equal to t, and the normal contact force is t d theta. Integrating the upward component of these forces along the semicircle will give us this expression, where in this step we have made use of the Capstan's equation. This is also why I call this part a sanity check rather than an alternative method, because this working requires the Capstan's equation, which we have derived in the first part. So if we have already done it, then we might as well do the first method. So this isn't as much as an alternative method as it is a sanity check in order to make sure that physics still works. Also note the difference between the friction and the normal contact force. The friction has a sine, whereas the normal contact force has a cosine, and the reason is because they are perpendicular to each other, hence the different trigonometry. Now let's evaluate this integral, and it turns out we need to use the double integral by parts trick. We obtain the following. We see that we actually obtain the original integral attenuated by a factor of mu squared. So letting the original integral be I, we can shift this I over to the other side, and solving for I would give us this. Now what is this I integral that we have just calculated? It's the lift provided by half the semicircle of string. So in order to calculate the total lift, we need to multiply that by 2, and equating the total lift to mg, we obtain the following. So what we've basically shown using our calculations is that for part B, where there's friction involved, friction actually does part of the lifting as well, because you can see that there's a vertical component. If not, we've come to the end of this question. If you have any comments, please leave it in the comments below, and leave a like and share it with your friends if you found this useful. Thank you.